I want you to look at these two trees right here. Okay, these two. Can you just spend about 30 seconds, convince yourself each tree on the left and on the right, they are both binary search tree. Okay? And I'm pretty sure what you're now calculating in your mind is to do in order traversal, right? To see if that's sorted sequence. If you're doing that, definitely on the right track. Okay? So they are both binary search tree. Yeah, you can also verify maybe after class as well. But I can take my word for that. However, we call this tree over here on the left balanced. But we call this one here unbalanced. We'll define exactly what we really meant by balanced versus unbalanced a little bit later today. There's some mathematical property we're going to study, but we'll get there a little bit later. So let me just give you some intuition. So this is called a balanced binary search tree. And this one here is what we call unbalanced. Okay? And then, first of all, both of them are binary search tree. So let me call this one binary search tree number 1 and binary search tree number 2. Okay? And both of them, if you do the in order traversal, you're going to get exactly this linear sequence. Okay? You can also double check. You can take my word for that for now. Okay? I'm going to write it down here. So if you do the in order traversal on binary search tree number 1, it's going to give you just the same order as the in order traversal of binary search tree number 2 on the right. And the order is going to be exactly just the array A that I have over here. Okay? And by the way, the equality here is not really assignment, just about mathematical equality. The contents are the same. Okay? I just want to show to you, even though the in order traversal result is the same, but the actual tree structure is actually very different. That's the main point. Okay? But I'll dive a little bit deeper into it. And let's do a little bit more analysis here. When we talk about binary search tree number 1 here, the number of nodes, if you count, is going to be 15. Okay, just 15. You can take my word for that. And what is the height of the tree? What is that? Anybody? What's the height for this tree? That should be the log n. Well, that's what we're going to conclude. But what about exact number? What's the height? 5. Okay, good. Okay, maximum depth, right, of the descendants of the root. So if you try to count over here, so you got 1, 2, 3, 4, 5. Maximum. All right. So the height over here would be just equal to 5 and roughly big O of log n. Roughly. Okay. On the other hand, if you look at the right-hand side, the number of nodes is the same. But now we're looking at the upper bound for the heights. And that one, the height is about, okay, you can see that over here. So 1, okay, let's see here. 1, oh, sorry, don't count external nodes. 1, 2, 3, 4, 5, 6, 7. 7. And it's about n over 2, which is log, oh, sorry, not log, beg your pardon, big O of n. That's the heights, okay? So we're talking about logarithmic heights and also linear heights, these two. And let's now do some very important comparison. Let's say I'm trying to do a search on either case. And for each search, I'm going to see the corresponding search on the linear sequence over here. And then we're going to see exactly the following. For one of them, the search is going to correspond to a binary search on the sorted array. The other one is going to correspond to a linear search on the sorted array. That's a very important comparison to make. But let's see exactly. Okay. So let's say for the binary search number 1, let's say I'm trying to search for 80. Okay, let's say I'm searching for that, right? And for that one there, let me just wipe this out. Let me do it from scratch again. What's going to happen is, so I know that I start from here. 80 is larger than that. I'm going this way. So that means I start with 44 over here, and then I'll go to the right-hand side. And then identify 88 over here. 88 is about here. And then 80 is actually less than that, so I should really go to the left. So I essentially go to this part over here. And then I got my 65, which is about here. And then I search for 80, so that should be larger than that. So I basically go for this part over here. And then I got 82. And then that one there is actually going to go to the left. And then I got 76. And that one there should really go to 80, right? So basically, go to here. And then I found it right here, roughly speaking. So you can see the way I'm visualizing it, it's just like a binary search on the sorted array, like how we did it before. You just narrow down the search space about a half each time. Exactly, right? So this one tells you, when I perform the search on this particular balanced binary search tree, it corresponds to a binary search on a sorted array, which is log n. Number one. Okay, let me write it down first. So searching 80 on the binary search number one is just like performing a binary search on the sorted array A. So this is a very important insight, number one, log n. Let's now try to do a similar search, but on the right-hand side, BST2. That one there is not going to be that efficient, and we'll see exactly how bad it is. And for that one there, let me again try to, show to you. Okay. So let's see here. We are trying to search for 97. Okay. So for 97, larger than 54, go to the right. Larger than 65, go to the right. Larger than 76, go to the right. Larger than 80, go to the right. Larger than that, go to the right. Larger than that, go to the right. Larger than that, go to the right. And we'll get here. Right? That's actually how we go. And let's see how that corresponds to the array. So start with 54. And then we go to 65. And then we go to 76. Go to 80. And then we go to 82. We go to 88. We go to 93. And we go to 97. How does that look to you? Linear search. We're basically like writing a loop and go all the way from left to right until we find it. There's no like a binary search, any kind of pattern there, right? So that one tells you whenever when you do a search on a binary search tree, it's not necessarily going to correspond to a binary search always. It might just correspond to a linear search, okay? So for that one there, I'm going to say the conclusion here. So searching 97 on BST number 2 is also a binary search, but because of its shape, it's just like performing a linear search. A linear search on A. Right? Linear search, which will be linear. All right, recap, and then we'll take a short break. When you do a search on a binary search tree, it might just correspond to either a binary search on the corresponding in order sequence, or it might correspond to a linear search on the corresponding in order sequence. It depends on how balanced the binary search tree is. And after the break, very shortly, we're going to see exactly how to define what we really mean by tree being balanced. There's some mathematical property we're going to study. Okay, so just before we do the insertion deletion, we'll do that. Okay, so let's now just quick some summary. Okay, this will also help, especially for the deletion. Okay, let me just summarize about the different some property for BST. Okay, binary search tree. Okay, right here. Okay, let's say we have the root over here called P, parents. And then we got left child and we got right child. So following the left child and following the right child. Over here, right? So we may have some further subtree down here, right? Arbitrarily big. So we got left child and right child right here, okay? So here, let's say this is another binary search tree right here. So it's called LST, left subtree. And this one here is just another binary search tree as well. It's called a right subtree. Oh, let me draw better. Okay, this will be the right subtree. Okay, so far so good. And of course, if you want to do some in-order traversal, we know that it's going to be somewhere LC and P and the RC, right? That should be in that order. But let's go for other special nodes as well. This can also help for later. So let's say I want to identify the leftmost node of the left subtree right here. Let me call that N1. Okay, and then I want to have another node here. This will be the rightmost node of the left subtree. Rightmost in the left subtree. Okay. And we have over here N3, and then over here we got N4. Okay, you can think about N3 here. Similarly, N3 is the leftmost in the right subtree. N4 is the rightmost in the right subtree. Right? So we got N1, N2, N3, and N4. Okay? So I think that these nodes, let's try to think about how they should be positioned in the in-order traversal. And then we just try to identify them and talk about some property. Okay? So if I do some in-order traversal, okay, let's say try to do that. What will be the first one? N1, yeah. N1 followed by this, LC, followed by this, followed by that, followed by this, followed by that, followed by that, right? Okay, let's write it down, right? Of course, there might be some nodes in between, right? Which we don't really care at this point, okay? So we got N1 right here. And then we got some nodes in between. And then we got the left child. And we go to N2. Okay, and then we go to P, right here, the parents. And after that, we got N3. We got some nodes in between. We got the right child. And finally, we got N4. Okay, so let's now try to look at them and see, okay? Well, it's actually quite obvious, you know, in the actual sequence. This one here, obviously, is the minimum. And this one here, N4, right here, is the maximum. Okay? And then, let's now try to look at N2 and N3 somehow, relative to P. Okay? One way to say that is something like this. N2 over here is the largest key. That is smaller than P. From the sequence point of view, you can see N2 come right before P. Guarantee N2 is smaller than P. However, among all the keys that are smaller than P, N2 is the largest, right? Also, if you look at diagrammatically, P is here. So somehow this is a left subtree. Every key in the left subtree is guaranteed to be strictly less. That's a search property. However, among them, this here, the rightmost one, is the largest one, but it is still less than this. This is important, especially when we do the deletion, we have to look after this case. Okay, we're going to do that. Okay. Guys, any question? Good? Okay. Okay, let's now just finish this one here, and then we'll take a short break. Okay, and then we'll do some insertion. Okay. And then you can also look at also this one here, N3, right? It can be argued in a very similar way, because we know every key right here is going to be larger than this, but N3 is the smallest one. Everything in the right subtree guaranteed to be bigger than P. But N3 here, being the leftmost node in the right subtree, is a minimum. Right? So what we'll say is smallest key. That is larger than P. Okay, question? We're good? Okay. Let's see. So I would suggest we try to do some very quick visual example for insertion. Okay? And then I would suggest for today, we will only cover insertion, and then we talk about rotation right away. And then for Wednesday, we'll talk about deletion. I think that'll be better, right? So we wouldn't have to review insertion, deletion, which might take even longer. I really want you guys to see some rotation, which is completely new. Okay? So for insertion, just before I present the example, it can partially address what your fellow student question was. So for the binary search method, we don't really return null. One of the main reasons is when you return some external nodes as part of the insertion procedure, that kind of external node can be turned into a new node right away when you actually haven't found the item to be searched. Okay, we'll talk about it. There's some code just for doing binary search. You can take a look, very straightforward. So I don't really go over them in the class, but it's a recursive method. Okay, we'll talk about, okay, so for insertion. So for slide number 9 over here, so I'm going to let you guys study that. Slide number 9, you just talk about what's the running time for doing binary search on a binary search tree. Overall, it's going to be corresponding to the heights of the binary search tree. But the height of the binary search tree is there's no guarantee about its height. It may be linear, it might be log n. So you got to be careful. So once we talk about rotation, that's the way to maintain the tree balance, the tree heights to be balanced, like a log n. Okay. So this slide here, I'll let you read the facts. It's slide number 9. Okay. I'll let you read it. Okay. Insertion. Very quickly. So whenever you want to do insertion, the first step is you got to do a binary search. Okay, you got to do binary search. And the binary search is going to return to you either internal nodes if it has found the key, or it might return external node if it has not found the key. We're going to handle these two cases separately. Okay, so you can also read the slides about the different steps, right? It's kind of specified in a very clear, like a bullet point, so you can read them. Okay, I'm going to demonstrate to you about the two different cases. And the running time here, watch out, right? So when I say the insertion here, I didn't say log n. I just say big O of h. And the h is the height of the tree. Unless you have some guarantee about the height being log n, you cannot really claim that, right? So here, it really depends, okay? So let's now do very quick 2 examples, and then we'll take a short break. And then we'll do rotation after the break. So let's say we try to insert either 28 right here, or we try to insert 68 right here. That's what we try to do 2 insertions. And for case number 1, you can see 28 exists right here. But for 68, you can double check, it doesn't really exist in this particular tree. So we got 2 different cases. Okay? For case number 1, I can simply say 44, because 28 less than that, so we go to the left, 17. 28 larger than that, so we go to 32. And then 28 less than that, we go to the left. So, we have, so here, this is the note that's returned. Okay, so this is the P that we're talking about, right? So this, in this case, we simply replace the value, in this case, Suyang over here. Simply replace the value by the arguments. You can think about each node here stores the value and the key. So in this case, we don't change the key because the key does exist. So we just replace the value here, Suyang. Okay? Simple case. And the second case here, 68, it doesn't really exist, but here it's very important which external node is being returned. That's something we already showed to you in the previous page. Okay? So let's see. So we got 44, start with the root, 68, larger than that. So we go to the right. 68, less than 88. So go to the left. 68, larger than 65. So we go to here. 68, less than 82. So go to the left. 68, less than 76. So we go right here. So this is the external node that we're going to return, not null. So this means what we can do is we can now try to convert this particular node into some internal nodes, right? So this is unsuccessful search. So what we do is we are going to turn this external node here into some internal nodes. You can think about in Java, you're just going to create a new node right here, right? I'm just going to write down the whole new node, right? That new node there is going to have the 68, the key, and also the value. Let's say Una here, right? That's what you would do. You simply convert this external node here into internal node. And then at the same time, you want to make sure it has a left child and also right child. Both of them are just external. Okay, so that's after the insertion. So you can think about every time you want to do insertion, first of all, try to make sure the key exists or not, right? Once you know, then you will know whatever case you got to deal with. Okay with this? Okay, good, awesome. Okay, for deletion. Let's go over the principle one by one, case by case. Okay, so there are 4 cases in total. To be fair, it's more like case number 1, 2, and 3, but for case number 4, it has 2 subcases, either 4.1 or 4.2. So we're going to go over 5 cases in total. So 5 examples. Okay, we'll see how many we can do today. Right, so in order to delete something, you got to make sure the thing you want to delete may or may not exist, right? So part of it, you still want to do a binary search right here. Okay, so you can see this is the binary search that we have to do. So the binary search we do is going to take the starting node. Oh, sorry. I thought I closed that already. Okay, sorry about that. Okay, so we're going to do the binary search. This will be the root, the starting point. And the key is something we want to search for. So that will be the key of entry to be deleted. Okay, so that's what we're going to do. And when you actually call this binary search routine or method, it's going to return to you P. And a P here, according to what we learned from the binary search, it can either be internal or external, right? If that's internal, that means the key exists. If that's external, that means the key does not exist. Okay, so case number 1 is actually what you will hope for, right? So you can see for case number 1 here, if the node that's returned is simply external, that means what you want to return, what you want to delete doesn't even exist in the tree. Nothing to delete, do nothing. Awesome, okay? But that's one case. Let's see this case right away, okay? So let's say here, we have the tree. You want to delete the key 31. We're going to do a binary search. So 31 less than this, so go this way. And 31 larger than that, so go this way. And then 31 less than this, so go this way. And then 31 larger than that, go this way. And 31 larger than that, go this way. right? So this is something that's going to be returned. So the key doesn't even exist, nothing to delete. It would be as if you simply want to delete this external node, which is going to do nothing, right? So nothing to do. That's case number one, simple. So key does not exist. In which case, do nothing. Nothing to delete, basically. Okay, awesome. All right, let's see case number 2. For case number 2, the key, let's see. The key actually exists, first of all. So this one here, we basically say P itself is internal. However, both of its child nodes are external. What does that mean? What that means is, for case number 2, what we are saying is, the node that we want to return, or we want to delete is called P, right? Let's say that's a node we want to delete. That's internal. However, both of its child node is simply external. This is also very easy to delete. Basically, when you delete this particular node, you don't need to worry about handling these two external nodes because they don't store any key anyway. You can just delete it without worrying about the consequence. All right? So there's no, once I delete this node here, these subtrees are called orphan subtrees. But in this case, these are just external, so you don't need to worry about them. Okay, so just remove the P itself. Okay, let's see. And the question is it still a BST? We're going to see. Okay. Let's now take a look at case number 2. Okay, so we start with 44 again. So 44 is less than 80. So we go to the right. And 80 is less than 88. So we go to the left. So 80 is larger than 65. So go to the right. And 80 is less than 82. So go to the left. And 80 is larger than 76, so we go here, right? So this is the node that we want to delete. And according to the algorithm here, the node that's being returned from binary search is called P. So we call this node P. Okay? P is something we want to delete. And it's matching case number 2 because these two external nodes are these two nodes are simply external nodes, right? If you think about it in order traversal, what are we doing here? So let me just try to narrow down the in order traversal that we can do. Why don't we just look at just this particular part? Well, actually, how about this? Let's now try to look at this particular subtree. Just this one here, okay? Let's now consider what's the in-order traversal for that. That one there is going to be, okay, start with 54. Okay. We start with 54. And then 65. And then 76. And then 80. And then 82. And then 88. Right? There might be keys after that and also keys before that, right? Well, we only focus on that particular subtree as the in-order traversal. And we want to delete 80. So after that, 76 is here, and also 82 is right here. All you do is just delete it. Basically, you can just basically turn this one here into some external node. That's all you do. So the right child for 76 right here is not going to be set to some external node. That's all you got to do. And the reason that this will work is because if you look at the new in-order traversal, I'm just deleting 80. So I still got 76 followed by 82. Whether or not it's still balanced is another story, right? We're going to handle the balance rotation by another phase. This phase here, just want to delete. Okay. All right, any questions? Good? Okay, good. Let's do case number 3, okay, at least for today. So for case number 3, what we have is this. So what we have, we still get P, but we only got one of the child nodes is internal. That means one internal and one external child. That's what we have, right? So for case number 3 over here, what we have is, we have the P that we want to delete. One of the nodes could be left or could be right. Let's say it's left, it's internal. But the right child over here is external. Okay? And then there might be something underneath it, right? So in this case, how do we somehow delete P? But in this case, you may have to worry about, oh, what about, once I delete this, what about its left child? Because it's internal, right? So I got to worry about that. So we're going to see exactly what to do. It turns out it would just be okay. Just return. So we talk about something called R. I'll show you what R is in the algorithm. Okay. The R is the child of P that's internal. So this is R right here. Okay, this is R. So what we are saying is, all you do is, you can simply replace the value of P just by R. But we'll see exactly how to do that, right? That's what you will see in the algorithm. Just replace the P by R. But how do we replace it? We'll see. Right? Okay, let's see. Let's now take a look at case number 3. Right here. So we want to, let's say, delete an entry with the key 32. Right here. Okay, how do we delete it? So 32 is less than that. So we go to the left. And 32 is larger than 17. Go to the right. And 32 is right here, right? According to the algorithm, this is called P. You can see its child nodes. One is external, the other one is internal. That's why we are matching case number 3, right here. Okay? And we call the internal child R. That's what we have. So this is called R. Right? So what should we do now? This case here is not too bad. Okay? Basically, what we can do is, there's several, you can think about conceptually. We want to somehow replace the 32 over here just by the 28. How exactly do we do that? Okay? So we may have to somehow, first of all, delete this link. And then 17 over here is going to set a link to be this one here. Okay? And then this one here might just be garbage collected at some point. We don't need to worry. You just stay disconnected from the tree. Okay? 2-step. So this will be step number 1. You want to get here, and step number 2. Right? That may be something like a Java code you can think about. Yeah?
Do we need step number 1? Like if I just said 17.next is equal to 28, like there's no reference to...
Yeah, I just want to be a little cleaner conceptually. Just want to make sure it's completely disconnected, right? Just diagrammatically. You want to make sure that one there is not a child nodes for 32 anymore. So that's why I want to do that. Yeah, may not be programmatically necessary, you're right, but we can just make it cleaner, right? Good. Yeah, awesome. It's a good question. Yeah. All right, so that's what we're gonna do. And how do we justify this? Very quickly, okay? So once this is done, conceptually, this will be gotten rid of. Okay, so this one will be done, right here. So now if you think about it in order traversal again, right? You want to make sure after each deletion, the in-order traversal is still going to give you some sorted sequence that is so necessary, right? Let's say this part over here, right? Okay, let me finish this part here and then we are done, okay? Just bear with me 1 minute or 2. So the in-order traversal before the deletion. The in-order traversal before the deletion. So we got 17 here, followed by 21, followed by 28, followed by 29, and followed by 32. Okay. So what we want to do is, we simply just want to get rid of the 32. That's what we want to do, right? Is this actually the new in-order traversal we'll see? Indeed, right? If you look at that, it's going to be 17 followed by 21. And then we go to 28. And then we go to 29. That's exactly right. Okay? Because now the 28 has now become the right child of 17. That's what you have. Okay? Just make sure you follow that one there. Okay? So now we got case number 1, 2, and 3. So we spoke about case number 1, 2, and 3, so they are well understood. So I just want to talk about case number 4. Okay? Somehow case number 4 will involve invoking also case number 2 and 3 as helper methods, somehow. All right? And in your coming assignments, which I'm going to release at some point, maybe around the reading week, I'm also going to let you implement the insertion and deletion for BST. I think it's also worth doing. Okay? It's something that we didn't really have time to really do in 2101, but I think in 3101 it's also a nice way to implement algorithms like this. There will be some implementation details you have to think through as well. Okay? That's something we'll let you try. It's kind of fun exercise, actually. Okay, for case number 4. Okay. So we say that the P here is really something that's returned by the binary search. Okay? And the P that's returned, somehow they got both children being internal. Okay? In that case, we just cannot just remove P, in which case both children are going to become, they call orphan subtrees, right? We cannot do that. Okay? So both are internal. So we're going to see an example. Okay? So both are internal. So the idea is like this. Okay? Let me draw something here right away. So let's say, for example, let's say the one we are trying to delete is R. So case number 4. Okay? I'll draw something just to sketch the idea. And this is actually something we also went through when we reviewed the BST. Okay? So let's say the R, okay, let's say right here. So for example, let's say this is the node to delete. For example. And that one there has 2 children, right? Both child nodes are internal. So I have one internal child over here. I got another internal child. And they might have arbitrary subtree underneath it. And now the question is, how do we somehow delete this guy here? Right? We want to delete this. Okay? So this is the P that we're talking about. All right? How do we delete it? Apparently, you cannot just get rid of it. That's not the way to go. Right? We're going to do some replacement. And to really see what kind of replacement we can do, you got to think about when we do in-order traversal, what comes before this node to be deleted, or what comes after. You can do either way. All right? So if you do in-order traversal, for example, right? Again, let's review. We have seen this diagram in the lecture, right? Just review that. Let's say N1, N2, N3, P, and then N4, N5, N6. And somehow the way I can label them can give you the order already, right? So if you do in-order traversal, you're going to go for the minimum, which is N1. And then at some point you will reach M2. And then you'll go to N3. N3 is going to be the largest key that is smaller than P. All right? And then you go for P, and then go for N4. Okay, let me just write it down. And then I'll talk about it. So just go up here, right? When we talk about in-order traversal, we got N1, followed by N2, and at some point N3. And then we got P, and then we got N4, and then we got N5, and then we got N6. That will be the sequence, okay? So the step is going to be something like this. Of course, you can read the textual description as well. I'll just show it to you. Okay, we're going to see 2 different cases, but they follow the same principle. The idea is we want to remove this guy here, but we cannot just remove it directly. What we do is we can do replacement. Either you can try to say, I want to replace the value over here and put it over here. Step number 1. You basically replace P by N3. I'm not removing anything just yet, right? And temporarily, you have N3 followed by N3, but that's okay. And then N3 over here has the special feature. N3 over here, for example, is the rightmost node in the left subtree of P, right? According to the geography, right? It's the rightmost node. If it's the rightmost node, there are only two cases, okay? N3 over here, only two cases. N3 over here, only two cases. Case number one. N3 may have just two external nodes. Or case number two, it may be that N3 has one internal and one external. So these are the only two possibilities. Okay? And one question which is on the slides. Is it possible, okay, so here's a question. Is it possible that we have N3 over here, and then somehow we got another internal nodes, and etc. Is it possible? How come? That's a very critical question, but I'm glad that's the right answer.
It would not be the rightmost node.
That's exactly right. All right? So it's very important. So this is something I want to point out, guys. So the reason that we got two sub-cases for case number 4, it says that either N3 over here has two external nodes right here, or has only one external node. You might be wondering, is it possible it has no external nodes? It's not possible, because if this is internal, then N3 wouldn't be the rightmost as we illustrated here. It's kind of contradictory. Right? It's a point you want to make sure you're convinced. All right, good. All right, so that's about the sketch. So what we do is, after we have done the replacement, we are now going to remove N3. So N3 here can either be removed in this case, or it can remove in this case. Okay, this case over here is really the case number 2 that we spoke about earlier. Okay, and this over here is really the case number 3 that we spoke about earlier. That's why I said it's more like a calling. The delete method is a helper method. That's something you will try when you do the assignment later. Okay. All right. So step number 1 would be to replace, and step number 2 is to just remove N3. So we only remove this guy here. We don't really remove this one here. That one there, we just replace it by as if we removed the key already. All right? That's really case number 4, right? We got 4.1, 4.2. Why don't we do that very quickly, and then we'll take a short break. Okay? Yeah, really take a look at this slide here. It really summarizes all the 4 cases you got to handle for deletion. But let's now do exercise here. Okay? So let me just identify which node we're going to remove in, question. Go ahead, please.
So in the case where N3 has one internal, one external,
Yeah.
if you replace P with N3, what happens to P's internal child?
So here, okay, sure. So we're basically talking about this case over here, right? Okay, so good question. So let's say we are running into this case, but we're going to see that anyway, but I'll mention that conceptually. So let's say we are in this case, and where N3 actually got, let's say, some internal, and also, okay, sorry, let me draw it again. It got some internal, and also it got some external. What we can do is, we can simply replace this value, let's say this is x, put x over here, and then remove it. That's what we can do. That's exactly what case number 3 would do, which you can review. But I'll do that again here. Okay? Good. All right, let's now talk about these 2 cases. So we want to remove 17, right? So let me ignore the binary search process because you know how to do it. Question?
Can you replace P by N4?
Yes, you can. Okay, that's good. It's actually one of the also exercises I put there. Okay, I'll put it here for you. Can R contain the smallest key such that it's larger than right? That's exactly the question here. So guys, another point for you. Here we are saying we replace the P by N3. Can we replace P by N4 and then delete N4 instead? The answer is yes, you can. Because in terms of in-order traversal, N3 goes before P and N4 goes after P. So if you want to do the replacement, as long as it's go right before, right after, you'll be okay. But don't do both. Okay? So either you simply replace P by N3 and then delete N3. Solution number one. Solution number two, you can replace the P by N4 and then delete the N4. It's also going to be guaranteed the way N4 is going to look like. But of course, you're going to define the solution accordingly about which case you want to involve. Right? Good question. All right, let's now do these two examples, and then we'll take a short break. Okay. So let's say 17 that we want to delete, right? 17 is right here. And the path we're going to follow will be, so from here and then all the way to 17, right? So we want to delete this guy here. So this is P. And let's say we want to delete N3 right here, right? It's going to be the rightmost node in the left subtree. This is the left subtree of P. And the 8 here happen to be the rightmost node, right? It's actually a very simple tree, but that one is just the rightmost node, okay? Rightmost internal node. This is the rightmost internal node. Okay, let me just pause over here, and then let's see another case, okay? How about we want to remove 88? So we're going to say 44, and then go to 88, right? So let's say that's the one we want to remove. So this one here, we got 88. So this is the P, all right? And then we want to find out in the left subtree. Okay, let's identify the left subtree right here. This is the left subtree of P. And then we know that this 82 is the one we want to replace. So 82 over here, right, is the rightmost internal node. So this one here is the rightmost internal node. All right? And we're going to perform the two steps the same way in these two cases, right? Number one, we're going to replace this node here, replace its value for this. Also replace its value for that. That one is going to preserve the in-order traversal because they are the predecessor of the 88, right? The in-order traversal. So step number one. So step number one, we're going to replace 17 by 8. Temporarily, we got duplicate, but that's okay. Temporarily. And then, also, step number one here, you're going to replace 88 by 82. Okay? And step number two, we're going to delete the duplicates. Also, delete the duplicates, right? This case, easy, because the node we want to delete already only got 2 external child. You can just delete it. This is case number 2, okay? So delete this one here. Delete 8. And this is case number 2 in our algorithm, right? Exactly case number 2, when both child nodes are external. Case number 3 is one of them is internal, okay? So now this one here, we want to delete the 82. And that one there has just one internal child, in which case you can simply, again, you can replace 82 by 76 and then delete 76. Well, that's what you can do, right? Okay, I'll let you do that one, okay? So this one here is number 2, delete 82. 82, okay, I'll try to write better. 82, and that is case number 3. Okay, So just remember, for case number 4, you will have to somehow also call either case 2 or case 3 to terminate that particular case. Okay, just remember. Okay, so I would say before the assignment is released, at least get yourself very convinced and understood about the principle over here, about the 4 cases. So when I release the assignment and let you program the insertion deletion, you just gotta have this page ready and have the example understood and then program it accordingly. There might just be some very minor implementation detail you have to watch out for, but it's gonna be very valuable exercise to do. Okay. If no question, why don't we take a short break, 3 minutes. Let's say we want to somehow construct a binary search tree by inserting the key values in this order. So think about, let's say this one here is the key, a key value. Okay. How do we insert that? So we start with 100. So we start with an empty tree. And then we insert 100 first. And then we want to insert 75. Now, 75, should it go to the left or the right? The left, right? Because the search property, right? So that one should really go to the left, 75, right? So far, this is a binary search tree because when you do an in-order traversal, you're going to get 75 followed by 100. It's a sorted sequence, right? That's how you check to see the search property actually is there. And then insert 68. It will end up being right here, 68. So you can see 100, go to the left, 75, go to the left, you got 68. Again, you get in order traversal 68, 75, 100. Okay, and then similarly 60, and then 50. Oh, okay, and then just 1. So now we got all the elements. So in this case, the number of element is 1, 2, 3, 4, 5, 6. Okay? What about the heights of the tree? The height of the tree is about the number of edges from the bottom leaf to all the way to the root. So we got 1, 2, 3, 4, 5. So the height is equal to 5, which is about n minus 1. So it's a big O of n. So this is just one simple example to show to you it is possible, if you're not careful, to really have certain insertion and then you have a certain sequence of insertion without any adjustment in between. You just got some tree of linear heights. And for this one here, linear heights, results in big O of n, search, insertion, and deletion. That's why you got to be very careful. So whenever you say you want to do binary search, all good. I got to make sure if you're implementing binary search on a binary, if you're implementing binary search on a binary search tree, you got to make sure the height itself is log n as opposed to linear. And you can try these 2 exercises, just to see, right? So it just gives you different flavors about how the tree can be created as not balancing. Okay, so these 2 will be exercises for you. Okay, give it a try. Okay, right here. And let's now take a look at the next one, which is about high balance property. So this one here as a formula, just to remind you about what does it really mean for the height of a particular node or a subtree. We're going to just use the example, but you can review the definition. Okay? So here is a high balance property. Let's go over that and I'll show you visually how you can do the exercise. Okay? So a binary search tree will be called a balanced. Okay, let me just write it down here. So when you say a binary search tree, and then plus the high balance property, That one there is going to give you a balanced binary search tree. And this one here, let's just take a look and we take some notes together. That one tells us every internal node, we only consider internal node, we don't consider external node. Okay? Every internal node, the heights of their children should be differ no more than 1. Okay? I'll write it down first and then we'll see how to see that visually. Okay? The difference for every internal node, for every n, okay, n is internal because he has at least one child, right? The difference of heights of n's children should be less than or equal to 1. Okay, there are two parts. Number one, we only consider internal. And then number two, we want to make sure the heights of their children should be different no more than 1. If there's more than 1, like a 2 or 3 or 4, we gotta watch out. Okay. So the idea would be as soon as the high balance property is violated, we should do something, which is called rotation. That's something we'll definitely cover next week about how you can do rotation. Okay. Okay, given this, let's do some quick annotation, just about exercise. We'll see. Okay, I'll just put this one down. Okay, so let's start with balancing. Okay, let's take a look at this. We'll look at actually 3 examples. I'll go over each one of them with you. Okay. So let's say this. The way to really annotate is this. So there's some conversion we're going to follow for the binary search tree. So we got internal nodes, which stores the key value. Okay, internal nodes, right over here. And then you also see that internal node also got some external nodes. External node will simply use a circle to really express. Okay, external node usually does not store any value just yet for the key. So this will be actually very useful. I'm going to review that part on Monday. So this kind of implementation will allow us to store things in here as a new key. Okay, that's something I'll review on Monday. But for now, let's just take it for granted. Okay. So the way to really check to see whether the tree at the moment is actually balanced. Oh, before that, is it a search tree? 5, if you do in order traversal. 5, 17, 32, 44, 48, 51, 56, 77. It's an in order traversal. It's a sorted sequence. So it's really a search tree. But is it high balanced? Let's see. The way to do it is you're going to somehow go bottom up. Okay? To start with, annotate the heights for each external node to be 0. So I'm going to say 0 here, 0 here, 0 here, 0 here, and also 0 here, 0 here, 0 here, 0 here, and 0 here. Okay? And for children at the same level, we can immediately consider what's their height difference. Okay? For example, you can see for these 2 siblings right here, what is the difference of their heights? 0, right? 0 versus 0. And also for these 2, the difference is also 0. Okay? And for these 2, the difference is also 0. And for these 2, the difference is also 0. We cannot go any further just yet because we haven't computed the heights for other nodes in the tree, but we'll continue. Okay? But at least as far as those pairs of the external nodes are concerned, their parent node, which is internal, is actually okay because the high balance is not violated just yet. How do we actually annotate the rest of the node? According to definition, the height of a particular node, if that's internal, is going to be 1 plus the maximum heights of its children. Okay? What will be the heights for this one here? The height of its children is 0 and 0. What's the maximum? 0. And then plus 1. So its height will be just 1. All right, let's try this one here. What's the height of these internal nodes? Maximum heights of its children, 0 and 0. Maximum 0 plus 1 will be 1. Okay, and then this one here, 0, 0, maximum 0 plus 1, we get 1. What about the height for this one here? 2, because here the children, 0 and 1, the maximum is 1, and then plus 1, you get 2. Okay, hopefully you get the idea. And 0, 0, maximum 0, and we get 1. And then 1, 1, maximum 1, plus 1, 2. And then 2, 1, maximum 2, plus 1, you get 3. Okay, 2, 3, maximum 3, and then plus 1, you get 4. All right, that's about calculating the height. I would say you don't necessarily have to consider the height difference just yet, maybe until you actually figure out the heights for all the nodes first. Okay, maybe figure out the nodes heights first before you actually talk about difference. Okay, and then let's now talk about the difference, right? For example, you can see over here between these two siblings, the difference is just 1, which is okay, less than or equal to 1. And then the difference right here is actually 0. Right? You got 1 versus 1. And the height difference over here, 2 versus 1. So the difference is 1. Also fine. And then you got the final level here. These two sibling nodes, the difference is 1. Right? So we also fine. And this one here, just itself, so we don't need to consider. So far you can see for every internal nodes, their child nodes have the height that's with height no more than 1. So the height balance property is nicely satisfied by this first tree. Okay? It is balanced. So what we'll do now is we're going to insert one node. And this insertion here, let's see if the insertion itself is going to make a tree that used to be balanced, not balanced anymore. All right? So we basically start with the same tree. All right? And then I'm going to show you explicitly, right? So with this tree here, the heights that we calculated, I'm just going to put it here, right? That's the height we just calculated. And we're going to see how the height is going to be changed along the way. Okay? So this one here, just let me annotate as well. So that's also 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, like that. Let's start with this. And then we want to insert 55. Oh, actually, insert 55. Where should 55 go? This will be some insertion routine I'm going to also review very quickly on Monday. Okay? So basically, you want to think about where should 55 go. 55, you do a binary search. 55 should go to the right, right? Compare with 56, you should go to its left, 55, right? And compare with the 48, 55 is larger, so it should go to its right. And for 51, 51 compared with 55, 55 is larger, so we should go to the right. So this is the external node that we retrieved. So that means 55 should be stored in this particular external node that's returned. Right? It's a very quick summary, but I'll add more slides to really show you the review. Right? That's something you can also take a look. So what's going to happen is we're going to actually create the 55 right here. Okay? So this is going to be the inserted 55. That one's going to be internal. Accordingly, we should also get 2 external nodes right here. Circle here, and also circle over here. And we got 0 and 0. What we should do now is very critical, right? Since we have inserted one node into the tree, we need to update the heights along its ancestor path. we need to update the heights of the nodes along the inserted nodes ancestor path. And we know the ancestor path is actually along this way, right? Along here. Let's update the heights, okay? Let's start with this, okay? So let's see this. Let me use maybe purple, okay? 0, 0, so this means this should be 1, right? And then we got 0, 1, this should be 2. And then 0, 2, maximum is 2. So this one should be 3. And then 3 and 1, maximum is 3 plus 1. So this should be updated to 4. 2 and 4, maximum is 4 plus 1. We got 5. Guys, follow so far? Right? So we inserted one node to the bottom of the tree because the key doesn't really exist. And then we try to update the heights along the ancestor path. And now we need to identify if the tree is actually still balanced. And whenever you identify the tree being unbalanced, maybe it resulted from some insertion or deletion, you ought to find the lowest point when the tree becomes unbalanced. Let's see. Okay? So let's go this way. So this will be also part of the procedure, how you're going to do rotation when I'm going to cover on Monday. Okay? Let's say this. So 0, 0 here, I think the difference is fine. The difference over here is simply 0, so we're okay. And now here, you got these two siblings here. You got 0 versus 1. So difference is 1. We are also fine, right? However, if you look at these two, we actually got 0 versus 2. So the difference over here is 2. So this is definitely the earliest point where we see that there's a violation of the high balance property. Give me 1 minute, I'll finish up. We'll do the rotation next time, okay? And then you can keep going if you want to. You can definitely see that here we got 3 and 1, right? If you look at these two over here, the difference is actually 2, which is also violating the high balance property. And finally, if you look at 2 and 4 right here, the difference is actually 2. So that tells you there's also another violation. So we got 3 occurrences of the violation. So this node here has the heights of its 2 children larger than 1. And also this internal node over here has its 2 children, the heights difference more than 1. And also for this node as well, because the children height also differs more than 1. All right? So that's really something we want to fix. So immediately after this insertion here, we want to make sure the balance of the tree is restored right away before we take on any further insertion or deletion. That's this slide here, slide number 23, is just about the steps for you to do some insertion. Afterwards, you may actually have to do some rotation. I'm not saying you have to do rotation always. You only do it when necessary. Okay, let's go over some bullet point quickly, and then we'll see one example. Okay, so let's say after you have inserted some new node n, you know how to do insertion. That's something we just covered before the break. You're actually going to somehow go along the ancestor path for that new node being inserted. Go over that ancestor path all the way up to the root. If you don't find any unbalanced node, that means your insertion is pretty good. You haven't caused any unbalanced. In that case, you don't need to do anything. So case 1 is something you will hope, but most likely not in the test. I might just give you some case where you have to do some work, right? So case number 2, that's something we're going to do together, okay? But just notice that you might have run into case number 1. Maybe that should be some conditional, maybe in your implemented Java code. All right, case number 2. Let me just go over some very important terms and variables, and then we'll do one example altogether, right? So let's say you try to go along the ancestor path of the node being inserted all the way up to the root. The very first node you found that's unbalanced. Notice that the very first one, okay? The very first one is you're going to call it A. Okay? And then from there, along the ancestor path, A's child should be called B. A's grandchild should be called C. Okay? We got A, B, and C. Okay? Identify A, B, and C. Once you have done this, you're going to look at how A, B, and C are slanted. If A, B, and C slanted to the left, do a right rotation. If A, B, and C slant to the right, do a left rotation. You might be thinking, what about it slant to the left and then to the right? And then you got to do a right-left rotation. That's something we'll see as well, right? So it really depends on exactly how A, B, and C are slanted. So we've got different ways to handle. But for today, we just do one, okay? All right, so here, if they slant the same way, you got to do a single rotation. But if somehow they slant different ways, maybe left, right, or right, left, you got to do double rotation. Double rotation, we're going to see that maybe on Wednesday. All right, let's now do one example here. Okay, so I'll talk about this one. That could be a nice summary, maybe for next time. Let's just do left rotation. Okay, so now you got your piece of paper with your tablet computer. Can you first start? Let's do this exercise together, right? I'm going to do it on my iPad. Okay, what I want you to do is this. You want to start with an empty binary search tree and insert this sequence of keys, 44 followed by 17 and then 78, etc. Right? Build that binary search tree. And don't forget, all the external nodes should be like a box, right? Like how we said. And then annotate the heights for each node. Okay, that's what you're going to do. How about spend about 2 minutes doing this? And then we can go over the answer together quickly. Okay, I'm going to do that on my iPad as well. Okay, in about 1 moment, first of all, I would like to show to you about the tree first before we annotate the heights, right? Done? Yeah, it is easy, right? Okay, guys, how about this? Can we at least agree? This will be the nodes. All right? Okay, good. And now, just don't forget, for every internal node here, don't forget, you may have to draw the external node right here, right? Just don't forget. This is important as part of the step. Okay, and then the next step will be to annotate the heights for each node. Okay, just take 1 minute or so. Okay, just 1 moment. You shouldn't take too long to annotate the heights. Go bottom up. Is this something you're getting? I hope. Okay, let's double check, right? We got 0, 0, and then we got 1. 0, 1, we got 2. 0, 0, we got 1. 0, 0, we got 1. 0, 1, we got 2. And then also we got 1, 2, we got 3. 2, 3, we got 4. And quick check, is this tree balanced? Yeah, because if you check for every internal nodes, their child nodes have their heights difference no more than 1. For example, difference between these two is 1. Between these two is 1. Between these two is 1. Between these two is 0, etc. Right? There's no violation. Okay? All good. That's how we start with. And on the slide, it asks you to do a second step. Okay? Now, based on this, I want you to do the following. You may want to redraw the tree. Might be a little bit easier. So I'll call maybe B here. So you can copy the tree. Might be easier for me to do that. It's digital. So maybe just redraw the tree. Okay? Redraw the tree with all the heights, and then try to insert 100 into the tree. And then updates the heights of each node. And the only node you may have to update will just be along the ancestor path of the node that's being inserted. Okay, I'll show you that one. So I'm gonna switch to the slide. I'll let you try. Okay, so insert 100. Okay, should take you not too much, more than 1 minute. But for that one there, just for the purpose of recording, I'll just do it from scratch with you. But I just want to make sure you can do it. Okay, insert 100. Okay. If you want to insert 100, you basically want to do a binary search for 100, right? So 44, go to the right, 78, go to the right, 88, go to the right, 95, go to the right. So this will be the external node that's returned from the binary search. Agree? Okay? So once this is returned, we're actually going to insert 100 right here. So the way I can do it is by doing this, right? So I'm just going to delete that external node that's returned. And then I'm just going to say 100 being inserted. From there, I have 2 external nodes. Okay? That's the insertion. And then when I need to update the height of the tree, I only need to focus on the ancestor path. So 100 is inserted, basically focus on right here. Okay, focus on this ancestor path. So think about this is the ancestor path of the inserted node. Okay, let's now update the heights. Again, let's go bottom up. So we got 0, 0 here, and this should be 1. Okay, so here we got 0, 1, and this one here is not 1 anymore, right? It should be 2, right? So this one here should be 2. And then we got 0, 2. What should this be? 3. All right? You can see it's unbalanced already, right? So this one here should be 3. Let's keep going. Okay? And then we got 1, 3 here, and this one should be 4. So we got 2, 4 here. This one should be 5. Apparently, the tree is unbalanced. According to the algorithm that's on the slides, right? We ought to define, okay, let me just show you again the slides, okay? So what we need to do is we want to find the lowest unbalanced node along the ancestor path for the new node, okay? Let's say this. In the slides, we actually said this 100 here, okay? I wouldn't write it up, I just want to wave a little bit quickly. Here, we call this the n. Okay, you will see the variable n in the slides, right? That's the node that's being added, the new node. Okay, so let's now go bottom up to see where is the lowest node that's unbalanced. Okay, is this node unbalanced? Is it? No, because 0, 1, the difference is 1, right? Go up 1 level. Is this node unbalanced? Yeah, exactly, right? 0, 2, the difference is 2, right? So this is the very first node or the lowest node that's unbalanced. Okay. Okay, let's now isolate it right here. Okay, right here. So this is the lowest node. Lowest node. That is unbalanced. Okay. Now here comes a very important thing, right? The very let's go back to the algorithm here, and we call that A. Accordingly, we're going to find B and C. Okay. First of all, let's identify A. So this is A. This is A. The B should be the child of A. However, you might be thinking, should it be the child here or the child over here? It should be along the same ancestor path that we are following. So now, along this ancestor path, the child for A is right here. So that's B. Okay? So this one here is B. And this one here is C. A, B, and C. Okay? Apart from that, so now we got A, B, and C right here, right? A, B, and C. A, B, and C, they're slanted this way to the right. That means we should do a left rotation. We should do a left rotation on the middle node of B. I'll give a little bit guidance here, and then you can give a try before Wednesday. Okay, I got about 2 minutes. Should be enough for me to give you guidance. Now you want to focus on just this subtree here that's rooted at A. We got A, B, C, and you can think about this guy here, this guy here, this guy here, and this guy here. In this case, we're lucky because they happen to be external node, but let's handle that in a more general way. Think about this one here, this subtree here is T1. This subtree over here is T2. This subtree over here is T3. And this subtree here is T4. Okay? If you do the in-order traversal, what do you have? You got T1, A, T2, B, T3, C, and T4. What we want to do is to make the middle node here as the root of this particular subtree. So this is something we want to do. All right? So let me do one more thing. Right here. You can see the ABC here is exactly the ABC here. And then we got T1, T2, T3, T4. We actually got T1, T2, T3, T4. Right? Let's see some quick summary about what you should do. So here, if you try to do some left rotation on B, basically B is going to become the new root right here. And then B itself should really got 2 children. It can be just A and C. Okay, let's see why. It can just be A and C, and then from there, we can also get subtrees right here. 1 here, 2 here, and 3 here, and, oh, sorry. Okay, just give me 1 minute, okay? I'm gonna wrap up, okay? This is important. Okay, so this one here can be just T1, T2, T3, and T4. Okay, so now think about the in-order traversal. The in-order traversal before and after the rotation will be identical. It's going to be just T1, A, T2, B, and then T3, C, and then T4, right? If you try to do the in-order traversal on this tree here, and also this tree here after the rotation, you will get exactly the same. Okay? So now, in order for you to finish right here, right? This is what I want you to do, maybe on before Wednesday, and then we'll go over that together in the beginning. You want to redraw the tree right here. And then you want to isolate just this part right here. And then do the rotation only locally on this particular subtree. After the rotation, B here should be the new root, and A and C, and etc. T1, T2, T3, T4, as I said earlier. Try to do that before Wednesday. So we said we actually got a sequence of keys to really insert into the tree. So what we got is right here, right? This one here, you can annotate the heights bottom up from the external to internal nodes. This tree here is balanced, right? So this one here, okay, let me just start with here, right? That's a new completed duplicate. So what we have is, for A here, it will give you a tree that's balanced, first of all, right? So this is a balanced tree. On the other hand, B here, after inserting 100, is going to give you something that's unbalanced. Unbalanced in the sense that if you don't really try to handle the unbalanced facts right away, you're gradually leading towards linear heights for your tree. Not necessarily right now, but in the long term. So you definitely want to handle that systematically. So after inserting 100, right, you can see 100 is right here. And then, so that will be the new node being inserted, and of course underneath it, you got two external nodes. And then we try to annotate the height bottom up again, right? For that process, I may not repeat. So you can see that right here. The height difference, you can see 0, 0, difference is 0. 0, 1, difference is 1. So 0, 2, over here, the difference is actually 2, right? So that's the first instance where we got the child node's heights will be more than 1. That means their parents, which is this node here, that's the very first node that's unbalanced. Okay, that's very important because you need to identify the lowest node in the tree that's actually unbalanced. Okay, so again, so you want to look at this node that's being inserted and follow along its ancestor path all the way to the root. And typically after insertion, you don't need to go that far. So it's not exactly log n for you to go all the way to the root, not necessarily. You might just want to go about 1 or 2 levels. It's more like a constant, okay? So once you go to identify this particular node here, that's be the lowest node that has the, I will make a quick notes here. So A here, this is the lower, oh, actually I wrote it last time, okay? The lowest node. The lowest node, that's actually unbalanced. That's the most important facts, okay? In the case of the insertion, we only need to do one single rotation. Well, the single rotation itself can be either double rotation or maybe single rotation. But when we do deletion, you may have to do more. That's something we'll see. All right, so that's where we ended up with, right? So let's now complete this, okay? So what we identified the other day was A, B, and C, right? So we got A, we got B, and then we got C, right? And then we got their subtrees, T1, T2, T3, and T4. And let's now remind us aside right away, and then we're gonna do rotation. So I'll put it here. So let's say we got A, and also we got B, and also we got C. Underneath A, we got T1. Underneath B, the left child, we got T2. And then we got T3 and also T4, right? That's what we have. What we want to do is we want to do a left rotation. We want to do a left rotation on B. So that means B is going to become the root right here. Okay, and then underneath it, we're going to get A here, and then we're going to get C here. And then we got T1, T2, T3, and T4. All right, you can double check. If you see the in order traversal for this one, T1A, you can see T1A, T1A, T2B, T2B, T3C, T3C, and then T4, right? Exactly the same sequence. So that's the right way to do. So you can always try to remind yourself before you actually do the concrete rotation. So just remind yourself how to do it. All right, so final step. I'm just going to just draw from scratch quickly, okay? So what I will do is I'm just going to put here, C. Okay, so I got 44 at the top, and then underneath it I got 17 and 78. And 17 has the external child here. And also we got 32. And then over here, okay, good. And underneath 78, I got 50. And then I got external and also external, okay? So think about this part over here is something I'm gonna change, this part here, okay? Just before I do that, let's now try this, okay? I'll use a slightly different color. So here I got 88, and then I got this. And then underneath it, I got 95, and then I got external, and then I got 100. And then underneath it, I got this, and underneath it, I got this. Okay? That's what I got. And let's now do the rotation. Okay? Let me just annotate one more thing, and then we'll do it. So this one here is basically A, B, and C. And here we got T1, T2, T3, and T4. Okay, how do we do the rotation? Somehow I'm using digital pages, so it's easier for me to do the illustration, but I'm gonna see how you can do that on paper. I'll let you choose whatever that works for you, okay? I'm just gonna set this aside. Okay, just this part here. All right. I know that, oh, I'm sorry. I know that I should really get B here. So B here is in the middle node. I need to get it right here. It's going to be the new root. And then underneath it, I should get A and C. I'm going to reconstruct the tree. I got A here, and I got C here. Okay, so far I have reconstructed only A, B, and C in this order. What I got left is T1, T2, T3, and T4. Right? I'm going to put them individually. So T1, T2, T3, T4. Okay, so I got T1 here, T2 here, T3 here, T4 here. So I got T1, T1, T2, T3, T4. Okay, so this one I don't need it. And finally, I can simply let this one here go back here. I'll put it here. And you can think about this part here, we'll just link to it. Like that. Follow? All right? Of course, you can draw better. I'm just running out of space to the right. Okay? And let's now double check. Is this tree balanced though? Right? We know that the in-order traversal is going to work. What about the heights? So if you look at that, so let's see. We got 0, 0, 0, 0. 1 and 1, right? This will be 2. So here, we got 0, 0, and then here we got 1. 1 and 2, we actually got 3, right? So 0, 0, 1, 0, 1, we got 2, right? 2 and 3, we got 4. Right, you can double check. The whole tree here, after annotation, is still balanced for every node. All right? Hopefully it's not too bad, right? Just get the big picture right. So usually, it will be somehow either given a tree like this, or you got to reconstruct a tree like this, right? Typically, one way. And after that, I might ask you to really do some operation. Could be insertion, deletion, or maybe a serious operation, right? Let's say this, in this case, insertion. After that, you got to update the heights. You only got to update along the ancestor path of the node being added in this case. And you will notice you want to identify the very first node that has become unbalanced. And from there, you got to decide which pattern you're going to do. In this case, because they all slant this way, so you got to do the opposite way for the rotation on the middle node. Right? That's what we got. All right. And of course, this part here is just a little aside. You can remind yourself. It's not really part of the answer, right? Just something to remind you right here. Any questions? We're good? Okay. So that's about doing some left rotation.